Alrighty, welcome back. We're on 5.2. You did a little bit of discovery learning in 5.1 dealing with exponential functions. We're looking here, we're going to be doing some graphing, and we're going to be looking at the characteristics of them, and especially bringing it back into our transformations. Alright, first one. Suppose a colony of bacteria doubles in size every hour. Well, speaking of bacteria, I know they're very good at mathematics. How do I know that? Well, I got this picture here. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. Hey, Donald, looks like these bacteria you isolated may be multiplying exponentially. All right, that's what we're looking at. Let's look at it again here. So anyways, initially there are 100 bacteria. How many bacteria would there be after 3 hours, 5 hours, 12 hours? Well, let's start looking at this pattern here. We know that the bacteria doubles every hour. So if we start at 100, that's times 0. That's at the beginning. After 1 hour, we're going to multiply that by 2. That's going to give us 200 of them after 1 hour. So at times 0 is 100. After 1 hour is 200. Then we take that 200 and they start multiplying, and they're going to double. And after 2 hours, we're going to have 400. Then those 400 start doubling, and after 3 hours, we have double of the 400. We've got 800 of them. Oh, it sure would be nice to not have to go through every step to get to our answer. So let's look at what's happening here. So if we start with the 100, we know that after the first time there, we're multiplying by 2. That gives us our first hour. Then after our second hour, what we're really doing is we're taking 100 and multiplying it by 2 and multiplying it by 2 again. Well, really multiplying it by 2 twice is like squaring it. And then in the third hour, we've got the 100 to start with. We're multiplying it by 2, then multiplying it by 2, and multiplying it by 2 again. We're multiplying it by 2 3 times. So it's 2 to the 3. Notice that the first hour is a 2 to the 1. The second hour is 2 to the 2. The third hour is 2 to the 3. So we should be able to go through and get right to 5 hours in one shot. So starting with the 100, that's the original, multiply it by 2 to the 5th, which gives us 3,200. And let's see what happens after 12 hours of these nice bacteria. Here we go, 2 to the 12. That is 409,600. Almost 410,000 bacteria in 12 hours. Yike, that's a little crazy. All right, let's do some work with the graphs. Let's look at what our graphs are. So using graphing technology, we're first going to start with the first set. Look at those 3, and then we'll look at the next 3 after that. So how do we enter that into our calculator? Well, take a calculator. Into y1, we're going to put 1.1. Good idea, put that in brackets. It's not necessary here, but it will be necessary as we go further along. Put that into brackets. To the x. And then we'll graph that and see what it looks like. So your first one, when we punch that in, should come up with something like looks like this. And you can see my scale there. I'm going from negative 15 to positive 15 on the x, and from negative 5 to 15 on the y. So that right there is y equals 1.1 to the x. What's important here to look at? As always, it's important to look at your intercepts. So let's start with our y-intercept. And our y-intercept, and we've got right there at 1 is our y-intercept. Well, let's look at our x-intercept now. Ooh, is not crossing the x-intercept in where we've got here. That looks awfully a lot like an asymptote. Well, let's keep going on and see if that is holding true. So after we graph the first one, we graph the second one, 3 to the x. And on the same grid there, you can see we've got y equals 1.1 to the x. And then we've got in blue there y equals 3 to the x. Let's again look at those intercepts. The y-intercept, even though it kind of looks like that blue one kind of goes right along it, it's just with our scale. It's getting ever so close to, but it ain't crossing it. That's an asymptote. And then, ooh, look at the y-intercept. They both have the same y-intercept. Interesting. Let's look at the third one, see if it can shed some light on this. Oh, again, we've got the 3 of them now. So now we've got y equals 10 to the x. We've got y equals 3 to the x. And we have the original y equals 1.1 to the x. And again, no x-intercept, but our y-intercept here, we've got, again, 1. Look at those bases from the exponents there, from the powers. 1.1, 3, and 10. It seems to be, as that number is getting bigger, our graph is getting steeper. All right, let's graph up this 0.9 to the x and see what happens there. When we punch that in, whoa! It looks almost the same as what the 1.1 to the x looked like, except it seems to be going in the other direction. But again, that y-intercept, there at 1. Let's look at the next graph. So we've got in this one, we've got the y equals 0.9 to the x. And on top of that one, we graphed y equals 0.5 to the x. And again, noticing the important part, that y-intercept is the same at 1. And no x-intercepts here. Again, asymptote. All right, let's finish this off with looking at the third one. We've got the y equals 0.9 to the x. We've got in blue the y equals 0.5 to the x. And now we've got the new one, which is in green, at y equals 0.1 to the x. And let's look at what's happening with the bases again. And it might be a little bit easier to recognize what's going on if we change those bases into a fraction. So 0.9, that's 9 over 10. 0.5, hey, 1/2. But let's take it to 10. Let's say that's 5 over 10, just for keeping the common denominator. And the third one, that's 1 over 10. Ooh, look at what's happening with the steepness of these ones as I go with the numbers. You can either look at the decimal or with the fraction. Make that connection there. So I was sitting at my desk there saying, what am I going to say to these students about exponents and the exponential functions? And I thought, I know. Mark my words. You harness that negative power of yours, and you can make it to the top just like me. Hey, I really like this though here. I'm not just over one. I'm over everyone. Hey, there's that negative exponent right there. And I love this diploma here on the wall. Lead coefficient. Third polynomial in a row. So that brings it back to our cubic polynomials that we were factoring there. So what is that exponential function? Well, first, in the most basic form, we're looking at y equals a to the x, where a is a positive constant. So a has to be positive. We cannot deal with a negative. And we should be able to kind of look at that further as we go along as why it can't be negative. So let's look at this first one. What happens if the a is greater than 1? Those are the first three examples. The 1.1, the 3, and the 10. Well, when we graph that, we notice here that it is increasing. If it's a greater than 1 number, it's increasing. We call that a growth. Now what happens if we're between 0 and 1? Remember, we can't go into the negatives with that a value. So if we're between 0 and 1, it's going down. It's decreasing. Okay. Decreasing, that is decay. We've got characteristics of these graphs now. First thing, the graph has a y-intercept of 1. And you should say to yourself, myself, why does it have a y-intercept of 1? And you say, okay, thank you, that was a great question. How do we find y-intercepts? Well, y-intercepts are when x is equal to 0. So let's plug in a 0 into there. So then we've got y equals a to the 0. Anything to the exponent of 0 is 1. So y equals 1. So every single time it's of this form, when x is 0, y is going to equal be 1, and that means the y-intercept's at 1. Now the graph approaches the x-axis but never touches it. That's a horizontal asymptote with the equation of y equals 0. Okay, well, let's go through those same motions there. Really what we're doing is we're saying, where's the x-intercept? Let's find the x-intercept. You find the x-intercept when y equals 0. So let's plug that into the equation. So we've got 0 equals a to the x. And now we're saying to ourselves, what value of x will make this 0? Hey, let's use a number so it makes a little bit more sense to us. Let's just randomly pick 2. So 2 to the what is 0? Well, 2 to the 0 is 1. And then what number can we use? We can't use, even if we put a negative value in for x, 2 to the negative 1, that's 1 over 2. That's 1/2. We can never get it to 0. There's nothing that we can put into x that will make this equal to 0. Because of that, we've got the horizontal asymptote. So the graph does not have an x-intercept system. The domain, we can plug in anything for the x, xer. But our range now, it is everything above this asymptote line on the x-axis. So it's greater than, but not equal to, just greater than 0. Again, taking your thinking deeper. Is there any way, any possible way to take y equals a to the x and have any other y-intercept other than 1? I want you to think that through. And also be thinking, if you can't, can you change the equation at the beginning to make it work so you can have something other than 1? Do a little bit of thinking with that one and write it down. Also, the next one you want to work with. Okay. What would happen if you put a of 1, if you had y equals 1 to the x? Write down there and see what kind of function, punch into your calculator, see what happens. Alrighty, it's time for your bit.ly link. Bam, there it is right there. Don't let them fool you on this one. Not true. Which one's not true? So go through, pound in there, which one of the 4? All right, let's do our first question now. And we're going to graph this baby and answer those questions. Well, let's get the graph going. So first and easiest way to graph this is just to do a table of values. So let's hammer that down there. Let's randomly pick some things. Pick some negatives, pick some positives, pick 0. We're just going to use the classic -2, -1, 0, 1, 2. You can choose whichever ones you want if those aren't the ones you like. All right, well, let's work that through. So first of all, we're saying y equals 1/3 to the, and we're taking in and putting -2 in there. Gotta remember what that negative exponent is on that picture there. The negative exponent, that means take the reciprocal of the base. Negative exponent, take the reciprocal of the base. And reciprocal of 1/3 is 3/1. That's where there. I'm over everyone to the +2. So we got 3 to the 2, so that's 9. Do the same thing with -1. Y equals 1/3 to the -1, which means take the reciprocal of the base. That's 3. Then anything to the 0 we know is 1. 1/3 to the 1 is 1/3. 2 to the 1, sorry, 2. 1/3 to the 2, there we go, that's what I meant to say, is 1/9. And we will graph those up. I'm feeling a little bit lazy, so I'm going to just use the answer graph. Oh, there we go. So we've got the first one at -2 and 9 right there. We've got the -1 and the 3. Boom. We've got the 0 and 1. That's our intercept. And we've got the 1 and 1/3 right there, and also the 2 and 1/9 way down next to it there. So it should look like that. Now we ask the question, what happens as x increases by 1, what's happening to the y? Well, let's go to our table of values. That's where it's nice to have this table of values. We increase that by 1, increase that by 1, we increase that by 1, we increase that by 1. What's happening on the other side? From 9 to 3, you might say, hey, I divided by 3. I'm going to say a little bit differently. I'm going to say I multiplied by 1/3. And then I multiplied by 1/3, multiplied by 1/3, multiplied by 1/3. Ooh, 1/3. That's an interesting one. Good look here. Multiplied by 1/3, multiplied by 1/3. Ooh. Then we say when x increases by 1, the y is multiplied by 1/3. Now, is it increasing or decreasing? Well, that sure looks like it's going down. We read left to right. So we're talking about it as we go from left to right on the graph. It's decreasing. Intercepts. Well, x-intercept, there's none. There's no x-intercept. But there's a y-intercept, and the y-intercept we have is, we know that, it's y equals 1. Next one, equations of the asymptote. All right, well, our equations of the asymptote are really talking about, hey, there is no x-intercept, so there must be an asymptote there, and that is the x-axis, which is y equals 0. That's the x-axis. Okay, domain and range now. Domain. I can plug anything in for those x values, whatever I want. Positives, negatives, fractions, doesn't matter. You can put them in there, XCR. But for the range, everything is up and above that asymptote. So it's greater than 0. All right, let's think back to when we did sequences. We did geometric sequences there. And we're saying now, example 1, that 1/3, or their example of the 3x, that's somehow a sequence. So try to tie the two together. See how an exponential function is related to geometric sequence. All right, hopefully you wrote something down here. Let's explore that, because that's an interesting topic. Examination of a table of values for an exponential function illustrates another characteristic. When the change in the values of x is constant, meaning going up by 1 or up by 2 or whatever, the corresponding value of y forms a geometric sequence. So what this is saying is an exponential function and a geometric sequence go hand in hand. They are extremely related to each other. So like we did with the other one. On the first one, 2 to the x, we're going up by 1 on the x. And look at what happens with the y. We go from 0.25 to 0.5. Divide that. Hey, that's a 2. Or 0.5 to 1, that's a 2. That's a 2. That's a 2. That's a 2. We're multiplying by 2 each time. From our geometric sequences, that was an R, common ratio, of 2. And we've got that right from there. And let's look at what happens when we go with the 1/2. Again, 4 divided by 8 gives us 0.5, 0.5, 0.5, 0.5, 0.5. That means our R is 0.5, or 1/2. And again, hey, that's the same. Let's look at how these two are related. A 2 to the x and a 1/2 to the x. Well, we've got at an x of 1, we've got a 2. Well, let's look at, oh, look at this. A y of 2 is also there, but this time it was at an x of negative 1. We had a y of 4, just like a y of 4. Hey, that was at 2 and negative 2. Or 8 and 8, 3 and negative 3. And the same thing works with those decimal ones. So there has to be some relationship between the two of those. And this leads us into transformations. When we look at relationships between the same types of graphs, there must be some transformations involved. And that's what we've got going here. So we can talk about stretching and reflecting and translating here. Next one. If we've got x minus 3 for there, what we're doing is we're taking x and replacing it with x minus 3. And 100% of the time, doesn't matter what type of graph you got, if it's exponential or anything, if you are replacing x with x minus 3 every single time, that's a horizontal translation, 3 units to the right. And you can see that happening here. Same thing if we go on into our vertical. So in this case, we're taking our y and replacing it with y plus 3. And 100% of the time, if you replace y with y plus 3 in any equation, you've got a vertical translation this time, 3 units down. And you can see that happening in the graph. Notice that everything is moving down, including that asymptote line right there. All right, moving off from translations. The next transformation that we looked at was stuff to do with negatives. So here in this one, we're now taking it, and we've got a negative in front. Well, that negative did not come from the x. It actually came from the y. So what we did there was we took y, and we took it to negative y. And then we brought the negative over from the left side to the right side. Every single time you replace with y with negative y, you've got a reflection in the y-axis, or sorry, the x-axis. And that's what you can see here. As well, if you take your x and change it into negative x, that means that x is going to negative x 100% of the time. We've got a reflection again, but this time over the y-axis. And this brings us to what we just were looking at. We've got y equals 2 to the x, and we've got y equals 2 to the negative x. A negative exponent is the same thing as saying, hey, reciprocate the base and make it a positive. So 2 is the base, 1/2 to the x. So y equals 1/2 to the x is a reflection about the y-axis from y equals 2 to the x. And finally, let's look at our last transformation there. In this one, we've got 2 in front, which really came from the other side of the equation. It really came from y being replaced with 1/2 y. And I better say this right now, you cannot, you cannot multiply these two numbers together. That order of operations, you've got the x That's an exponent on that one 2, not on the other one. You cannot multiply them together, so you have to do the exponents first. Don't try to do that, please. So every single time you do y to 1/2 y, that's a vertical stretch by a factor of 2 every time. And you can see that happening here. Multiply every y value by 2. And then we've got the same thing happening if we put a 1/2 in there. I'll change that to stretch again. And same thing. You're multiplying every y value by 1/2 because it's vertical. And on to this one here. Now we're replacing the x with 1/2 x. So x goes to 1/2 x. And 100% of the time, if you replace the x's, that's horizontal. It's a stretch by a factor of 2. And you can see it happening here. Multiply every x by 2. And same thing, if we put in 2x, that's a horizontal stretch. And I'm using stretch because that's what's on your diploma. Horizontal stretch by a factor of 1/2. And that means multiply every x value by 1/2. All right, let's look at all these transformations that are going on in here. So first of all, we've got some stretching going on. We've got the c. That's talking about a vertical stretch. We've got a d in there. That's talking about a horizontal stretch. If those two numbers are negative, we've got also reflections happening. Yeah, negative. So that's saying if c and d are negative. And then we've got our translation vertically. That's our k value. And we've got our horizontal translation, our h value. Make a big note of this right now. Star that. Double bracket. You need that here in that exponent. Make sure it is so. And then at the bottom there, you've got your mapping notation, where your x goes to x over d plus h, and your y goes to cy plus k. Or in other words, use your transformations in the order that you've been taught. And here we go. We're going to graph this. We're going to use transformations. And that's really what they're asking you to do. But first, they're tricky. Hope you noticed that. Y equals, you got to double bracket that before we can get started. We need to factor out that negative. So negative bracket x minus 2 bracket. Make sure that you've got that done first. So here's where you got to look. It's going to affect the horizontal translation if you don't. Okay, so let's do our table of values. And we'll just use our classic. Negative 2, negative 1, 0, 1, and 2. And we've got y equals 2 to the x. So we're starting with our basic one. Plug in negative 2 in. That gives us 1/4, 1/2, 1, 2, and 4. Now, we're going to take those points. And we're going to use our transformations. So the first transformation we have, that's R3. So vertical stretch by a factor of 3. And in English, that means multiply all y by 3. Then we've got no horizontal stretch. Oh, but we do have a horizontal reflection. So that's a reflection about the other axis, which is a y-axis. And that means multiply all x by negative 1. And then we're on to our translations. There is no vertical translation, but there is a horizontal translation. And that's 2 units, and it's going right because we factored out that negative. That means in English, add 2 to the x's. Well, let's do that. is first of all take our original point of 2 common 1/4. Let's take that 1/4, let's multiply the y value by 3, that's going to give us 3/4, or 0.75 if you prefer. Now we're going to take our -2, multiply by -1, which will give us 2, and then to that 2, we're going to add 2, which gives us 4. Let's do the next one, same process. Take the 1/2, multiply the y by 3, which gives us 3/2, or 1.5 if you prefer. And then we take the -1, multiply by -1, which gives us 1. And then 1 plus 2, which gives us 3. Do the same thing. The 1 times the 3 gives us our 3. And on the x, 0 times -1 is still 0 plus 2, so we're at 2. And then 1 times -1 is -1 plus 2 gives us 1, comma, and the 2 times 3 gives us 6. And the 2 comma 4, same process, multiply the 2 times -1, -2 plus 2 is 0. And for the y, 4 times 3 is 12. Let's plot each one of those points. And by the miracle of technology, I've got mine right there. Nice and quick. So notice here that the y-intercept is not 1 this time. Oh, look at that. It's 12. And now we're going to ask, is that increasing or decreasing? Well, that's going down, that's decreasing. The intercepts, we just said it, that's 12. Equation of the asymptote. There was no vertical translation, so it's still y equals 0. Domain, still XCR. Always going to be XCR. And the range is going to be y is greater than 0 because the asymptote state. Now, we can find the y-intercept from a graph only when it's either in the table of values and it's perfectly in there. But if it's between 2 points and we have to guess and you have to estimate, graphically is not the way to go. We're going to have to do it algebraically. And like I said, to find your y-intercept, make x equal to 0, substitute it in, work it through algebraically. I've explained this a few times here, so make sure that you can do this type. Okay. Write something down for yourself now. Make that connection. All right, last example. Everyone's favorite, word problems. I know it's mine. I love word problems. Okay. Think of it as a game, not just a problem. Word challenge, that's a better thing. Okay, so for every meter below the surface of the water, the light intensity is reduced by 2.5%. The percent of light remaining at the depth d meters can be modeled by this function. Graph it. So first thing you want to do, we're going to punch it into our calculator. y1 equals 100 times 0.975. This way, we have to have the brackets when we've got the two different numbers, and we're taking it to the x. Let's punch that in and see what it looks like on the calculator. All right, so that's how you want to punch it into your calculator there. Now, it says we want to graph this. We want to see what the graph looks like. So we need to know what window to use. Now, this is a problem, and it's dealing with depth. And, well, we're not talking anything above the surface of the water. We don't know any information on that. We're only going below. So there's no point in going into the negatives with this. So we're just going to be starting how many meters below the surface. So don't go into the negatives with this question. We're going to start at an x is 0. And then, well, where is it going to start on the y-axis? Well, at d of 0, a depth of 0, if we plug that in, it's going to make it go to 1, and it's going to start at 100. So when we start picking our window, I'm going to go a little bit above that 100. Hey, 110 works for me. And then I'm just going to randomly pick an x maximum. I'm going to say 50 meters. I'm going more than 10 because part B says how many is 10 meters. So let's try that out, and let's graph it and see what it looks like. Okay, so we should get something that looks like that. And now it says, how far to 10 meters? what percent remains? Well, we're going to find the value at an x of 10. So go second, calculate, and we're going to use the value. That tells us what x value we want to use. And I want to use 10 for this one. And enter, and it tells me right there 77.632, blah, 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 which is approximately 78%. And now the next one says, when, or what depth is it going to be 50%? Let's go back to our calculator, and we're now going to do a y2 of 50. We're going to graph that. And we're going to say, where are those two going to intersect? And let's find the x value at that point. So second, calculate. Let's go to intersect. And is that the first graph? Yep, that's the one. Is that the one? Yep, that's the next one. And let's guess that up. Yeah, give me the right answer, though. And thinking, there we go, 27.377, which is approximately 27 meters. All right, and as always, finish her off, bring it together, hey, go with that deeper thinking, hey, make the connections for yourself, answer those two questions, and we'll